All right, let's talk about a classic coding problem, the sliding window maximum. And I know that might sound a little intimidating, but trust me, it's not. We're going to break down this really elegant, really powerful technique called the monotonic queue. It solves this problem in pretty much the fastest way imaginable. So let's dive right in.
So, why should you even care about this? Well, picture this. You've got 1,000,000 days of stock price data. Your boss wants you to find the highest price for every single 3-day period in that entire dataset. Now, you could check every single 3-day window one by one, but with 1,000,000 days of data, you'd be there forever. It's just way too slow. But what if you could do it all in one single lightning-fast pass? That's the power we're about to unlock. So here's the game plan. First, we're going to look at the slow, obvious solution, just to see why we need something better. Then, we'll introduce the hero of our story, the monotonic queue. We'll do a step-by-step walkthrough of how it works, prove why it's so incredibly fast, and then wrap things up with some pro tips to help you absolutely nail this in your next interview. All right, let's kick things off by looking at the way most people would probably try to solve this first, which, is a bit of a trap, the brute force method.
Okay, so first things first, let's make sure we're all on the same page about what the problem actually is. We've got a list of numbers, and we have this window of a certain size. Let's call it K. We put the window at the very beginning of the list, find the biggest number inside of it, and write that down. Then we just slide the window over by one spot and do it again, and again, and again, all the way to the end.
The most straightforward way to do this? Well, it's with nested loops. You have one loop that moves the window across the array, and for each position, you have another loop that goes through just the elements inside that window to find the biggest one. Makes sense, right? But it comes with a pretty big hidden cost.
And this slide really lays it all out. That naive approach has a time complexity of O(n) times k. That's because for almost every element in our array, we end up rescanning a whole window's worth of numbers. Our goal, though, is O(n), what we call linear time. We want to process the entire 1,000,000-day array in what feels like a single pass. And believe me, the difference between O(n) times k and O(n) is absolutely massive.
So how do we bridge that gap? How do we get to that O and N magic? Well, we need a smarter tool for the job, and that tool is the monotonic queue.
Here is the perfect analogy to understand this. Think of a line of people waiting to compete for a prize for being the maximum. Now, a new person shows up, and they're way stronger than some of the people already in line. Well, what's the point of those weaker people even staying in line? They have zero chance of winning as long as this new, stronger candidate is around. The monotonic queue works on this exact same ruthless logic. It gets rid of any candidates that have no chance of being the max anymore.
Okay, so let's get a little more technical. A monotonic queue is a special kind of queue that keeps all of its elements in a specific sorted order. For our problem, that means it keeps them sorted from biggest to smallest. And because it does this, we can find the maximum element, the champion, instantly. We just have to peek at the person at the very front of the line.
To make this whole thing work, there are really just 3 golden rules you need to remember. First, and this is super important, we store the positions or indices of the numbers, not the actual numbers. Why? Because we need to know when an element gets too old and falls out of the back of our window. Second, we have to enforce that sorted rule. The values at the indices in our queue must always go from biggest to smallest. And third, because of Rule 2, the biggest value in our current window is always, without fail, sitting right at the front of the queue.
Okay, rules are one thing, but seeing it work is another. So let's actually walk through an example, step by step.
We're going to use this array 1, 3, -1, -3, 5, 3, 6, 7, and our window size, k, will be 3. Our mission is to find the max of every 3-element chunk as we slide across.
So for every single element that comes in, we do 3 things. It's a simple little dance. First, we look at the back of our queue and kick out anyone who is weaker than the new element arriving. Second, we add the new element's index to the back of the line. And finally, we just do a quick check at the front to see if the oldest element is past its expiration date and needs to be removed. That's it.
All right, let's trace this out. The number 1 comes in, we add its index, 0. Simple. Next, 3 arrives. Well, 3 is bigger than 1, so it kicks index 0 out, and then we add index 1. Then -1 shows up. It's smaller than 3, so it doesn't kick anyone out, it just gets in line behind it. At this point, our window's full. The max is at the front of our queue, the value at index 1, which is 3. And that's our very first result.
Now watch what happens when the number 5 shows up. This is the magic moment. The queue currently holds indices for numbers that are all smaller than 5.
So when 5 arrives, it's so strong it just wipes the entire queue clean. All those weaker candidates are gone. Then we add its index, 4. This is that core principle in action. And now the max for this window is obviously 5. We just keep doing this all the way to the end.
Okay, this seems awesome, right? But I bet some of you are looking at that last step and thinking, hold on a second.
You saw that while loop, right? The one that pops elements off the back? I mean, we saw it clear out a bunch of elements at once when 5 came along. Isn't that just a hidden nested loop that makes things slow again? And that's a fantastic question, because the answer is what makes this whole thing so brilliant.
The secret is this simple number, 1. Every single element from our input array gets pushed onto the queue exactly one time, and it gets popped off, at most, one time. That's it. No element ever gets touched more than that.
This is the whole idea behind what we call amortized analysis. Think of it like this. Even if one single step does a little extra work, like when 5 cleaned house, the total amount of work spread across all n elements is still just proportional to n. Every element goes in once, comes out once, the work is amortized or spread out, which gives us an average cost of O1 per element, and that's what gets us to On overall. And when you look at it like this, the difference is just staggering. The naive approach is O of n times k. Even a smarter solution using a heap is O of n log k. But the monotonic queue at O of n is in a league of its own. It's not just better, it's the theoretically optimal solution. You literally can't do better than this.
Okay, so you get the concept. You see why it's fast. Now, how do you translate that knowledge into confidence during a high-pressure coding interview?
Look, it's easy to trip up on this under pressure, so here are the common mistakes to watch out for. Don't store values, store indices. You need to know when they expire. Always remember to check the front of the queue for those expired indices. Use less than or equal to when you're popping from the back, otherwise you'll mess up with duplicate numbers. And be ready to defend that O of n complexity with confidence. Now, if you really want to impress your interviewer, don't wait for them to ask. Bring these points up yourself. Explain exactly why this is better than a heap. Articulate that amortized analysis proof we just talked about. Casually mention that you can find the minimum by just flipping one comparison sign, and talk about how you'd handle edge cases. This shows you don't just know the answer, you understand the concept inside and out. And there you have it, the monotonic queue. It's a beautiful example of how choosing the right data structure can turn a clunky, slow problem into something incredibly elegant and fast. Which leads to a really interesting question. What other problems that you've seen that look like a brute force nightmare might be secretly hiding their own elegant linear time solution? Thanks for watching.